So we will go over the topology of OV4s. So first we'll define the definition of the OV4s and discuss differentiable structures on OV4s and covering spaces of OV4s, which is an important topic. So first of all, how do you define OV4? So is there a good way to express some quotient space like this, x mod gamma, where gamma has some fixed point, some elements of gamma as fixed point? We should do this locally. So remember our quotient space, like the pillow. So in fact, x mod gamma can be given an OV4 structure, but the OV4 structures are more general than the space of the form x mod gamma. Okay. So we want something more general than just x mod gamma. So let O be a host of second countable topological space. Let N be fixed. An open subset U tilde in Rn with a finite group G acting smoothly on it. G invariant map U tilde to O prime for an open subset of O inducing homeomorphism, G to O prime. So OV4 chart is such a triple U tilde G and psi here. So what is an embedding? Embedding is between these triple, so which is a smooth embedding from U tilde to B tilde, which induces the isomorph inclusion map UB for U phi U tilde and B for psi B tilde. So this is psi, sorry. Okay, so this is so inclusion is U tilde going to here, and then the V tilde going to be here, and then U is actually included here, and then this is lifted to I, and then the G will act, continue to act here, but the G will only be go to some subgroup of H here. So that's what inclusion is, and so equivalently, I is an embedding inducing the inclusion map and induces injective homomorphism G to H, so that IG is I star G for circle I for every G in G, and I star G will act on open set that is the image of this I. Note here, I can be changed to any H circle I for any H in H, and the image H circle I will be disjoint representative for disjoint representative H for this right coset group here. So we define this inclusion of the triples of model triples. So two charts are compatible if for any x in the intersection there is a neighborhood W of x in UVs, and the chart from W prime K U such that there are embeddings. So there are embeddings from this to these two triples. Okay. So so here you can see that if you have any intersection, then there's this model W tilde of the neighborhood point of intersection inside here, which gets included to here, and so that's the compatibility if that holds for every point in the intersection. Of course, this may not be a connected set here. So if you want to have some boundary, then you can allow U tilde to be the open subset of cross half space, and that will work, and that will define the boundary. So what is the definition of OV4? So so since Gx smoother is Gx freely on an open dense subset of U tilde. So an open OV4 atlas of X is a chart family of charts O tilde G phi covering X. So X here I mean the OV4 O tilde. I mean I think I switched notation here, but it still mean O tilde. So two overall atlas are compatible if the atlas is in one atlas, charts in one atlas is compatible with the charts in the other atlases. So atlases form a partially ordered set. It has a maximal element. So given an atlas, there is a unique maximal atlas containing it. So ovipole is X with this space with the maximal ovipole atlas. So one can obtain an atlas of linear charts only. So that is a chart where U tilde is on N and G is actually in the orthogonal group. So if we have U tilde with G acting freely, then we can drop this from atlas and replace with many charts with trivial group. And if you have any map from one ovipole to another, it's smooth if for every point there is a chart U tilde G phi with phi with X in X and the chart V tilde H V psi with Fx in B, so that Fu is in FB and F leads to this F tilde U tilde G as a smooth map. Okay, so then that's the smooth definition of smooth map. So two ovipoles are diffeomorphic if there is a smooth ovipole map with a smooth inverse ovipole map. So given X in all local group, Gx of X is obtained by taking the chart and then around X and finding stabilizer Gy of Y for inverse image point of X. Okay, so you just take the inverse image and then find the stabilizer there, and that will be the stabilizer of the point. So singular set is a set of points where Gx is trivial, and the subset of the singular set where Gx is constant is relatively close submanifold. Okay, so because of this property, O becomes a stratified smooth topological space, where the strata is given by conjugacy, fixed conjugacy class of Gx. Okay, so here, so stratified manifold means that it's a correct union of manifolds, but but each point is on a some smooth manifold. So unique smooth manifold here. So that's what you call the stratification. And the sub-ovipole y over ovipole x is an embedded subset such that for each point y in y and the chart b tilde g phi of x, for a neighborhood b of y, there is a chart y given by p g restricted to p psi, where p is a cross of manifold of b tilde and where gx1. And GP is an image of the restriction homomorphism to G to P. So this is a slightly more general definition than the usual definition, but we will use that. So the point is that G could act on some submanifold here, and then this will still give you a right definition. So to illustrate, let's go to some two ovipoles. So two ovipoles have only three types of singularities. So silver points in open arcs, isolated cone points, and isolated corner reflector points. The singular points of two dimensional ovipoles into three types. Okay, so these are mirror points where R2 mod G2, where G2 acts by reflection on the y-axis. So everything diffeomorphic to this, and cone points of order n is Rn multiplied by Gn, where Gn acts by rotations of angle 2 pi m divided by n for integers m, and the corner reflectors of order n is Rn divided by Dn, so where Dn is a dihedral group generated by reflections about two lines meeting at an angle pi divided by n. So here, the actions here are sort of isometry. So this is the mirror points, and then the quotient space will be something like this with this line in it. So this is called the silver point, and then these are dihedral group action, and the quotient will be some sort of wedge like this, and these will be mirrored. So this point will be called the corner reflector point, and this will be mirror points here. So for three ovipoles, the singularities are mirror points of a two-dimensional surface of silver points, or You could have a singularity in an open one-dimensional manifold where the models are given by some cyclic group fixing on axis, or the dihedral group acting on a plane times interval. So something acting on a plane, but you multiply by some interval. Okay. So in this interval, dihedral group doesn't act trivially. Or the singularity. Another one is a singularity on the end of three one-dimensional manifolds of singularity PQR, where PQR has these restrictions. Okay. So that's another possibility. And then singularity on a vertex where three silver surface meet with the edge being the three one-dimensional manifolds of singularity 2p, 2q, 2r, where PQR is restricted like this, or the isolated singularity of order 2. Okay, so it will be a situation like this, so where these PQR, three of them meeting, or you have these three meeting, but these are all silver, so we have some sort of a cone here near this singular point, and this is the singular point of dimension 0, singular point of dimension 0, and this will be dimension 1. So and then another one is just isolated singularity of order like this. So there's some order 2 singularity where it's obtained by quotienting with by the antipodal map. So actually the rank of this point will be RP2, but not the sphere. So these are from classifying spherical 1 or 2 orbipores, since links have these spherical structures. So examples of orbipores, manifolds are orbipores, and let G be a finite group acting on manifold M smoothly, then M mod G is a topological space with the orbipore structure. And so let Tn be M be the torus of n dimensional, then Gn will act with a generated acting by minus identity. So I more precisely something that induced by minus identity in Rn. Then for n equal to M mod G2 has a topologically sphere, and then it's 4 singular points. Okay, so this will give you 4 singular points, and for n equal to 4, we obtain some sort of Kuma surface with 16 singular points. So I don't think I want to go that deeply there. But there's another way to construct the report. So you take some smooth surface, and you take a discrete subset, and so for each point we take a disk neighborhood with this chart d prime gn to q, where d prime is a disk and gn acts as a rotation with 0 as a fixed point. And then we have we let q be this d prime to d as a cyclic branch cover. So you forget the usual chart, but you replace it with this chart. Okay, so then this point becomes a singular point. Okay, just by switching the chart. Okay, so then this is actually called the cone point type. So this will become a cone point, singular point. Another possibility is, so given a manifold with the boundary, then we can double it as a manifold and obtain G2 action. Then M has a orbital structure. So we have a manifold, and you double it, then you get a sort of closed manifold, or because you glue the boundary. And then since they are the same, you can act by G2. And then so this will be the manifold made up by the finite group case. Okay, so then this will mirror the. So this boundary now will be mirrored, consists of mirror points. And another is take a surface and the boundary be the union of smooth piecewise curve with corners. So this becomes surface with corners. So interior is given charged with trivial groups, and the interior boundary curves is given charged with G2 as a group. So this is called silvering. And corner points is given chart with some dihedral group as the group. Okay, So then this will make your surface into an OB-port. Okay. So this is doesn't change any set, but you're just changing these atlases, and that will give you a chart on OB-port structure. So embedded arc in the surface OB-port that's above, ending at 2 silver point, is sort of one OB-port. So as I said before, some minus identity will give you some sort of quotient like this, because these points will all be fixed, because minus identity will have to fix these 4 points, and up to quotient relations. And for surface, you can always put this cyclic atlas and then make it this into a singular point, and again for the corner points. Okay. So so if you have two Hilbert arcs, and then you can kind of join it by arc 2 1 over 4, and these are also Hilbert 1 over 4. It will all become a Hilbert 1 over 4. So this will be a one-dimensional sub-orbit. But of course, you need to put the structure so that the G2 action will preserve. So this will lift in the universal cover and the model cover as a smooth arc. Okay, so this part. Okay, so then this will actually become a silver embedded 1 over 4 here. So the vertex could be given dihedral group, and so something that's remaining arc will be actual boundary of the OB4. So here, so one thing different about this OB4 theory is in topologically this looks like a boundary, but if you give a silvering, then this is not really a boundary, because it has a chart which is actually the whole open set. So these are not the boundary. Topological boundary are not the boundary. So it's not necessarily the OE4 boundary. So I guess the OE4 boundary is actually a smaller set than the topological boundary. So in this case is for example, if you can kind of make these paths not silver, so silver this part but not silver this, then this will remain as a boundary. Okay, so this will be the true boundary, not silver. Okay, so if you silver this part, then these are not boundary. Okay, so that's an important distinction here. Okay, so let's talk about differentiable structures on OE4. So suppose we are given smooth structures on each utility G spice, so that the utility is given a smooth structure and G has a smooth action on it. So we assume that all the embeddings in the atlases are smooth, and M is given a smooth structure. So given a chart utility G phi, the space of smooth forms is space of smooth forms on utility invariant of the G action. So smooth form on orbifold is a collection of smooth form on each of the charts, so that on the embeddings they agree with each other. Okay, under these transition maps. Okay, so so one can define the integral of the smooth singular simplices into charts. This can be extended to any smooth simplex using partition unity and barycentric subdivision of the simplex. Okay. as before. So we can define also Riemannian structure, exponential maps, and curvatures without any problem, because you do it for these charts, and then they just have to agree on the embeddings. Okay, so when they have to be just compatible. So first we can prove the Gauss-Bonnet theorem also holds. So assuming that the X has a finite smooth triangulation, so the interior of each cell lies in a singularity with the locally constant isotropy groups, then we define Euler characteristic to be the sum of these plus minus sum depending on the dimension, but you have to divide by the order of the isotropy group here. So such triangulation always exists, proved by some people called Verona. So at least one people proved it. That's the reference I know. And the theorem is Allendorfer, Bayer, and then Hopf theorem is that if M is a compact Riemannian ovipolar of even dimension, then the Euler characteristic is given by this formula, where K is of course related to the Riemannian curvature, and OM is the volume of M sphere. So the proof essentially follows that of Choi for manifolds. Also, if X is finally covered by another ovifold, then the X Euler characteristic of X prime is R times the Euler characteristic of X, where R is a number of sheets for regular points. This follows since the sum of orders of local groups in the inverse image of the elementary neighborhood is always R times that of the group in the downstairs. Okay, so that's why you have the using this type of formula, you have to have R times of that. So okay, so let's define the covering spaces for ovifold. So let X prime be an ovifold with a smooth map P X prime to X, so that for each point X of X there is a connected model UG V, and the inverse image of VU is a union of open sets with the models isomorphic to UG prime pi. So points, so open sets in here, where pi u goes to UG prime is a quotient map, and G prime is a subgroup of G. Then P X prime to X is called the covering, and X prime is called the covering ovifold of X. So if you remember our pillow, then R2 is a manifold, so it's ovifold, and so here the UG G will be G2 here, and then this will be 3BR. Okay. So as an example, we can see that of a fiber product. Let me give you this example. So let Y be a manifold and Y tilde be a regular covering map with automorphism group gamma. So let's say it's free action. Gamma I is a sequence of some subgroup of gamma. Then let's look at the projection pi tilde Y tilde times gamma I gamma. So this is a right coset of gamma I to Y tilde. So this is just the projection. This part is just discrete set. So in this is, so if you quotient by gamma on the right action, by this right action here, then this will give you another right action on Y tilde. So this is Y. So this will give you a covering map. Okay. And this is actually the same as Y tilde gamma I going to Y, because if you see it, that because we are doing the right action, that only thing that so this so only thing that is the coset, the identity coset gamma I itself, and this which means this is identity, and if gamma is in gamma I, then that's the only thing that will actually make any action here, because in other places it will go to some other places, and then they're all going to be identical. Okay, up to some gamma I. So this is the same as this, but you can see it in this way. Okay. So we can do the fiber product by taking all these, and then you just producting this part only for each gamma I. And then you still define the left action by gamma by this. Sorry, this is a left action. I remember. I said it was right action. Sorry. And then this gamma I is the actually the right coset. Okay. And then the so right coset space. So under this you can see that this is actually the fiber product map. So fiber product is a product of these fibering maps, where the fibers, only the fiber parts gets producted. Okay, so that's you might not have learned that, but anyway, so that's example of a fiber product. So what is a developable OV4? So let gamma be a discrete group acting on a manifold properly discontinuously but not freely. Then we can find the collection of coverings so that the gamma I, where this gamma preserving xi is finite, and then if this is not intersection, and xi and xi is not has non-empty intersection, that only way that has to happen is in gamma I. So it acts on this xi, and this image of xi covers y tilde gamma. Then the x tilde gamma has an orbifold quotient of y tilde and y is called the developable. So in the above example, you can let gamma just be the discrete group acting on a manifold y tilde properly discontinuously, but maybe not freely. Then yf is fiber product of the this orbifold map. So you don't really need a free action here. You can do the same construction and obtain these fiber products of orbifolds, developable orbifold case. Okay. So that's one useful example here. So as an example, if you look at Dn linear dihedral group acting on a disk, then Bn Dn is given by a corner reflector orbifold structure. Then the maximal local group is Dn. So we can find the correction xi of covering, so the xi is of this form, or xi is Bn Cm, where Cm is a cyclic group of order m acting as a rotation. So this is a cone point. So so for a surface, we can always with the cone and cone reflector, you can always find these kind of coverings. And the mirror point is singular point with the stabilizer group G2 acting as a reflection. So we can always double on orbifold M with mirror points, so that the mirror points disappears. So so some doubling, this doubling covering orbifold is always orientable, but there are some other partial constructions where it doesn't have to be orientable. So Bi be the neighborhood of M with charge like this, and then define the new charge Ui times -1 y, and Gi by star, where Gix by Gixl, but this part is same, but you have to multiply by some sign. Sg is 1 when G is oriented motion, presuming G -1 if it's not, and G star is Gaussian map. And then there is a embedding from any embedding WH psi to WI GI phi, we can define a lift to here. So this will define embedding. So embedding will define gluing. So the result will be doubled orbifold, and the local group actions are orientation preserving. So the double covers. So this double covers original orbifold with Galois group C2. So in the abstract definition, we simply let x0 prime to be orientation double cover of x0, where gx on x prime by preserving the action here. So I should say this is G2. Okay. So for example, if you double a corner reflector, then you can obtain a cone point. Okay. So under this construction, the corner reflector becomes a cone point. So for the example, currently manifolds are over4, so manifold covering provides sample, and the pillow is actually covered by this torus. You can, or R2, which I discussed. So in this torus, we do pi rotation, then there are these four singularities where they go to the singular points. So if we double a corner reflector, we obtain a cone point. Thus, this with corner reflector is a double cover by the sphere with the cone points. Okay. So if you have a disk with the boundary, which is corner reflector, so if you double it, then you get a sphere with cone points in the corresponding places. Okay, that's what I mean here. So I should write more carefully. So we have some disk with the corner reflector. So if you do the double construction, then this will be doubled, and then there will be same places. It will be cone points of the same order. So if this was a 2pi order, then it would be, so dihedral group of order 2p, then this will be order p, and so on. And let's talk about teardrop orbifold. So teardrop orbifold is just a sphere with one cone point of order n. This cannot be covered by any other types of orbifold, so hence it is a universal cover of itself. And any sphere with two cone points of order pq which are relatively prime, so this is again a universal cover of itself. So if you choose a cyclic group action on Y of order m, fixing these two cone points, then the then Y mod GM is orbifold with two cone points of order PM and QM. Okay, so so teardrop will be something like this P, and then we haven't really told you how to compute the fundamental group, but there is no way to cover this by anything else. And then PQ with PQ relatively prime again. And then if there is some sort of a cyclic group action, then you can promote this to order having MP, MQ, like this. Again, I mean, of course, there's some cyclic group action you can do here also, like you could also get MP and then M here. Yes. So we will discuss the universal covering by using the fiber product. So universal cover of an orbifold is an orbifold y tilde covering any covering orbifold of y. So we will show that the universal covering orbifold exists by using fiber product construction. For this, we need to discuss elementary neighborhoods. An elementary neighborhood is an open subset with a chart component which whose inverse images are open subsets of the chart. Open subsets with the charts. So we can take the model open set in the chart to be simply connected, and then such an open set is of course elementary. Okay. So let's go to that case where you talk about fiber product of disk made up by some finite group G. So any covering will be Dn mod G1 for a subgroup G1 of D. So for this type of orbifold, given two covering orbifold Dn mod G1 and then Dn mod G2, covering morphism is induced by any element G such that G G1, G inverse is G2. So if you look at any morphism, then you can see that they lift up to Dn, and then this map has to be in the G because it both covers Dn mod G. Okay. So covering morphism is one-to-one correspondence with double cosets of form G2, G1, such that G1 is conjugated into G2. That's because if you multiply G2 by G by G2 element, then it doesn't change because of this. This condition doesn't change, and then if you multiply by G1 in this side, then again this condition doesn't change at all. So of course that these conditions are all satisfied. So the covering automorphism group of D and mod G prime is given by the normalizer of G1, G1 mod out by G1. Okay. So this is a very similar result to what usually happens in covering space theory also. So given coverings Pi, Dn, Gi go to Dn, G for Gi subset G for B homeomorphic to cell, we obtain this fiber product. So we have this type of covering, so we do it for Dn, and then you just do the fiber product to obtain a covering. So if you choose all the subgroup Gi of G, then any covering of Dn mod G is covered by VF fiber reduced by the projection to Gi factor. So you can do this for all the group, then any covering is going to be covered by this fiber product. So this fiber product will cover anything inside this product here. So that proves the universal probability. So we can do the same for a sequence of any collection of orbital covers of Y by patching over each elementary neighborhood. So for each elementary neighborhood, we do this construction, and then we patch them over construction. These construction, because these are canonical, you can patch these together. In this way, we can construct the universal cover by taking all the covers of Y. So we discussed the properties of the universal cover. So universal cover is unique up to covering isomorphism. So covering isomorphism is still defined very similar to the ordinary covering space theory, but with you have to consider the orbital structure a bit. And the group of automorphism, again, automorphism is defined very similar to the covering space theory, but you have to preserve the orbital structure. Is also called the fundamental group, and is denoted by pi1 of Y as before. And this deck transformation group acts transits beyond the fibers for each x and y. And so I should drop this on y tilde here. And then y tilde mod pi1 of y is y. So here, of course, this quotienting process will preserve the orbital structure, and then you get the descended orbital structure. So in this sense, this is correct. Any covering of Y is of form Y tilde gamma for a subgroup gamma of pi1 of Y. Again, the similar theory holds for covering space theory. And the isomorphism classes of covering spaces of Y is a set of conjugacy classes of correspond to the set of conjugacy classes of subgroups of pi on Y. So this is again one-to-one correspondence, okay, as before in the covering space theory. So it's exactly the same as you expect here. So as an example, how do you compute the fundamental group? So you have two-dimensional orbital, has boundary and silver points. Then you remove the open ball neighborhoods of some cone points and corner reflector points. Then the fundamental group of the remaining part can be computed by Van-Kempen's theorem by taking the open neighborhoods of the silvered boundary arcs. Okay, because they only intersect in trivial simply connected parts. So if you consider the components of these, so you just have to add by some G2 factors here. then you have to add the open ball neighborhoods, and then again using something very similar to Bankhampon, you can obtain the whole fundamental group here. Okay, so that's the so fundamental group of the three-dimensional orbital. Again, you can do it by removing first the zero-dimensional singularity and then one-dimensional singularity, and then you can do it with only mirror points, and then you add up the one-dimensional singularity, and then you can add up finally the zero-dimensional singularity. So it works like this.